Hey, this is chapter 25. It's about machining centers, some of the special things, topics related with machining centers, and lastly, is discussing machining economics. But I will not be discussing this intermediate sections. I will be only focusing on the machining centers, and lastly, I will briefly discuss the economics behind machining. We already discussed some types of machining centers, so I will not be spending too much time. I will just be showing you some pictures and mentioning about some specific equipment. We know that a machining center is a versatile machining machine so that you can perform various machining operations on the same machine. The thing is that you shouldn't be moving your workpiece from the table. So once you mount it onto the table, you can perform various operations. You can do drilling, milling, honing, tapping, reaming maybe. So they are all done on the same machine without removing the workpiece. So what we were doing in the earlier days, we were using many types of machines, and then what we were doing a single operation, then move that workpiece, place it into other station, do another machining operation, and follow the sequence many times, and this was not obviously efficient. We were consuming too much time on the transfer of the workpiece, on the mounting and demounting, but now with the help of such machining centers, once you mount your workpiece once, then many operations can be performed, even maybe at the same time if your machining center is capable of that. So they are highly versatile. It saves you money, saves you time. And in addition to milling centers, we also have some turning centers. Actually, the one we have in our machine shop may be called as an turning center. And let's briefly have a look at some specific components of these machining centers. The first one is the pallet. You can see some examples of pallets here. Pallets are mostly used to decrease the lead time, decrease actually the uncutting or idle time of the machine so that the machine will be doing machining all the time. So what we do, for instance, while some parts are being machined here, and some workers, some people are arranging other work pieces here, while the other pallet is being machined. So once this pallet is done, then with the help of automatic type of pallet changers, this is moved and new pallet is actually fed into this table, and then we can continue machining by maybe after just 5 seconds. So you're not consuming too much time in between the machining of different products. So it's called automatic pallet changer, and we know that there are also automatic tool changers. If you want to do several operations, here you see an multi-axis machining center. This is 5 axis. In addition to three translational motions, we have two rotational motions. So with the help of this extra degrees of freedom, you can machine, you can open highly complicated profiles. And it's another example of an machining center where we use multiple pallets at the same time. You see we have a pool of pallets, so we don't actually spend time for mounting the workpieces in between the machining operations. They are already mounted on pallets. So what you need to do, you need to simply move this pallet onto the table or to the underneath the cutter and start the machining process. We know that there are different types of machining centers. There are vertical spindle, horizontal spindle, or you may have some machining centers having both types of spindles, but obviously they are expensive. But the thing is that they're highly productive. You can machine any workpiece. And this is an example of vertical spindle machining center. We have this type, actually a similar version in our machine shop. As you see, they have usually automatic tool changers and control table, control panel, I'm sorry, work table. And in order to make it a sustainable manufacturing operation, They usually have such special chip recovery system. The chips generated are collected here and then recycled. It's another type. This is not milling center. This is turning center, but for components are almost the same. And if you have a universal machine center, then that means you are using vertical and horizontal spinners at the same time, maybe even using them on the machining of the same part. So with the help of them, manufacturing time can be decreased and can improve your overall efficiency. And we lastly have reconfigurable machines and systems. It's quite flexible, obviously, but a bit expensive and difficult to modify actually. For instance, if you look at these cases, what we do in such reconfigurable machines, we remove the table and then come up with a new table. But the main structure of the machine should always be the same. You may sometimes change the spindle. For instance, in A and B, we have a vertical spindle, but in C, we have a horizontal spindle. So depending again on your capabilities of your reconfigurable system, you may do such modifications so that you will be spending less time on mounting and you can decrease your manufacturing times. Now I will jump to machining economics, which is actually the last topic of this chapter. Why it's important since in manufacturing and machining, our aim is always to do the manufacturing machining in a shorter time at the lowest cost. So that's why now I will briefly discuss this issue on two plots. On these plots, we have actually cutting speed on the horizontal axis. And in the first one, we have cost per piece on the vertical axis. And in the second one, on the vertical axis, we have time per piece. So this one is about cost, and the second one is about machining time. Now let's focus on the first one. You see, we have a kind of an actually curve here. It is showing the total cost of a typical product and its relation with respect to the cutting speed. So I can say that the cost of the piece is a bit higher if you do the machining at a lower speed. And it becomes the lowest here, intermediate value of cutting speed, but after some point, the cost of the piece continues to increase. So we don't have a linear relationship. The relationship in between the cutting speed and the cost is a bit complicated. Why is that? Since after you increase the cutting speed to very high levels, what will happen? Then you will have more problems on your cutting tool. You need to replace them frequently. And that's why actually after an optimum cutting speed, the cost of your manufacturing machining increases. But to that point, the cost decreases since you are going to do the machining in a shorter time. Once you are spending less time, once you are spending less energy on machining, then that means your overall cost will be decreased. But as I said, after this critical point, due to the use of many tools, due to the frequent change of tools, we have an increase in the cost per piece once you increase cutting speed. Now let's have a look at some subcomponents of total cost. So I can simply say that this total cost is actually the summation of these four items. As you see, we have a constant term here. It's non-productive cost, so it's not related with the cutting speed. So that's why, regardless of the cutting speed, it's always constant. And this non-productive cost, we have some indirect costs like the overheads, the money you are paying for the building, the money you are paying for other auxiliary services. So that's why it's independent of cutting speed. Then we have machining cost. So once you increase the cutting speed, then that means you are spending less time on machining cutting. So once you spend less time on machining, and you will be consuming less energy, and you will be consuming actually less money. So we can say that machining cost is decrease. But the thing about the tool is that once you increase the speed all the time, and that means you'll be using the same tool for a shorter time. So you need to replace it more frequently once you continue increasing the cutting speed. And this tool change cost is somehow similar to the tool cost. So once you frequently change the tool, then that means you have more idle time of your machine, since while you are changing the tool, your machine will not be able to do machining, and your idle time will be increasing. So due to that, we will have an increase in the tool change cost. And once you sum all these, you obtain such a curve for the total cost of your machining. So in summary, I can say that we have an optimum cutting speed, which makes your cost actually the lowest. Now let's have a look at machining time per piece and its relation with the cutting speed. Again, we have some sub items. This time we have three components, sub-components, and if you sum these time values, you will obtain the total time required to machine a specific part. And again, as in the case of previous plots, we have a kind of a curve in between cutting speed and the time we are spending to manufacture a piece. And again, very similar. As you increase cutting speed up to some point, we decrease the manufacturing time, machining time. But after some point, after this optimum cutting speed, what happens? The time we are spending to manufacture the same piece increases. The main reason behind this increase is again the frequency of tool changing, since it affects our again idle time, since we need to spend time on demounting the tool, insert, and then replacing it with a new tool. So that's why it's always increasing. Once you increase cutting speed, due to the high frequency of tool change, we have a tool changing time increasing. And again, we have a non-productive time, which is constant and it does not depend on the cutting speed. And the other one is machining time. It's obvious that if you increase the cutting speed, then you'll be spending less time on machining. So once you again sum all these sub items together, you'll obtain such a curve giving you the overall machining time. And we now know that we have an optimum cutting speed, which results in the lowest machining time. But if you compare these two plots, we don't have actually a single cutting speed, which gives you the lowest cost and lowest machining time. So what do we have? Actually, we have a kind of an optimum cutting speed zone. So you should be actually keeping your cutting speed in between these vertical lines, and this is called as high efficiency machining range. So while you are machining these pieces, your cutting speed should always be in between this range. So increasing it above this range or decreasing it above this range is not meaningful, since if you decrease a lot, then that means you'll be spending too much money and your time will be too much. So it's meaningless. Or if you increase it to very high levels, then again it's not meaningful, since you'll be spending again more money and you'll be spending more time. So in overall, this is the range you should always be using. Your cutting speed should always be in between these two values.